Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hello again everybody. In this talk I'm going to be talking about Barrelfish, which is a research operating system that I was involved in for a couple of years. So again, I'm not going to be telling you about any particular kind of concepts that you might want to take away, but I'm going to be describing this research operating system and how we dealt with the challenges of modern multi-core architectures. Okay, so the basic problem, the starting point for this work was that the operating systems that we use today are actually not very well suited to what we anticipate for hardware in the near future and in the long term as well. The way operating systems are structured means that they don't scale well as the number of cores increases. They don't handle the increasing diversity of hardware. You saw yesterday how hardware was very diverse in the past. A lot of people anticipate that it will become increasingly diverse in the future as well. And the other problem with operating systems today is that as hardware evolves, because of their structure, because they're very large, complex pieces of software, it's actually very hard for the operating system developers to keep up as the hardware changes. So, optimizations that are tuned for one type of hardware have to be retuned for a different type of hardware, and so on, and that can be a very complex procedure. So I mentioned this yesterday, but the basic premise that I'm working from is that computer hardware is looking more and more like a network. By that I mean there's a high communication delay between cores. The cores can come and go with power management, etc. And the cores are not necessarily homogeneous. They can be of different types within the same system. And as a consequence, we, as in the members of the Barrelfish team, believe that the operating system should be structured in a very similar way to a distributed system. So in order to articulate this idea about structuring an operating system as a distributed system, we invented a reference model, which we called the multikernel model. So it's basically a writing down of the way in which we think operating systems will need to be structured for future hardware. And it's based on 3 design principles. So the first one is explicit message passing. So the basic assumption is that all communication will be by message passing rather than by shared memory. A hardware neutral structure, so we're advocating that you don't want to be designing your operating system to be tuned for the hardware that you anticipate it will be run on. And replication of common state. So instead of sharing common state as the default, we're saying you should replicate it. So Barrelfish is an implementation of the multi-kernel model. Okay, we invented the multi-kernel model and we built Barrelfish, and in fact we did both of them at the same time. But we believe that the abstractions that we're talking about in the multi-kernel model can also be implemented by, there are different ways to implement them, and that will become clear later. Okay, so the outline of this talk, I'm going to start by looking at multi-core hardware today and the diversity of it in particular. Yeah.
So, in the previous slide, you said that you want to send messages and in some sense shared state is replicated. Now, if I take both of those things. Me as an OS designer, if I want to do something, I can either keep my state in the replicated store, or I could pass messages.
Mm-hmm.
So can you give some more overview on when you will send messages and when you will keep something in the replicated state?
So, similar to clustered objects that I mentioned yesterday, it's really going to depend on the nature of that state and how it's going to be used. So, state that partitions well and where most of the accesses will be local. Obviously, you want to replicate so that you have fast access to the parts of that state that are relevant to the local core. In other cases, you almost certainly want to have some kind of server process and be sending it messages. That's an implementation decision, and in fact that's part of the reason why Barrelfish is not the only way to implement this model. But I will go through these design principles in more detail, so hopefully that'll make that clearer, yeah. I will show you examples, actually. Okay, so I'm going to briefly talk about multicore hardware, and then I'm going to talk about how the characteristics of this hardware challenges the way that current operating systems are structured. And then I'm going to go on and describe the multi-kernel model in some more detail, followed by the Barrelfish operating system itself. Okay, so what we've had up until now is Moore's law being a very reliable predictor of increases in computing speed. Moore's law states that the number of transistors on a chip will double roughly every 2 years at pretty much a constant cost. And this is basically because of advances in semiconductor technology leading to them being able to increase transistor density. And in fact, it's been pretty reliable since 1965, which is quite amazing. So this graphic is, which I think I took from the Intel website, is just showing the year of introduction on the X and number of transistors on the Y-axis, and highlighting some particular chips there. So a lot of people have observed that there's some problems with Moore's law continuing the way it has done since 1965. So the improvements that we see are driven specifically by increases in transistor density, increases in clock frequency, by power savings per transistor, and various techniques to exploit instruction level parallelism. All of these things are running into problems, and basically it's like a big red flag saying, well, Moore's law isn't going to continue to hold. First of all, the power wall. This is a kind of cute picture showing somebody frying an egg on an AMD Athlon. Okay, so what's this really talking about? Well, one of the things that drives Moore's law is that we can increase clock frequency. However, clock rate and power are correlated. So the power dissipation depends on the clock rate and on the voltage. Increasing the clock frequency means more power is dissipated, so more cooling has to be required. Correspondingly, decreases in the voltage can compensate for that by reducing the power consumption, but then you get more static power leakage. So either way, we're running into the limit of being able to cool commodity microprocessors. next problem is known as the memory wall, and this is talking about the growing disparity of speed between the CPU and accessing memory, especially memory outside the CPU chip. So because of these increases in disparity, memory is basically becoming the bottleneck. So in 1985, with a 1 megahertz CPU clock, it only took 500 nanoseconds to access memory. Memory speeds have grown about 10% a year, and CPU about 55%. So obviously there's a problem. And it's interesting to contrast this with the first system I talked about yesterday, the C.MMP, where the memory speeds were hugely greater than the CPU, and they had a different. And then there's the ILP walls. So instruction level parallelism is basically a bunch of techniques to reorder and pipeline instructions, which basically makes things go faster. However, it does require some more complicated hardware, so it increases the complexity there. And also increases the power consumption, and so we're back to the same problem. And essentially, the performance improvements that we can get from ILP have stopped increasing. So this phrase "power wall plus ILP wall plus memory wall equals brick wall," I think comes from a report by Berkeley by Dave Patterson and other people. So to summarize, we can't make processors faster. Performance is dominated by the time to access memory, and while accessing that memory, the stalling of ILP improvements means that the processors can't keep busy while waiting. So as a consequence, we're moving to multicore. The improvements in speed that everybody expects are coming from having multiple cores. So multicore processors, it's basically the future of computing, or even the present. I don't think Microsoft has shipped a uniprocessor version of the operating system since 1996, I believe. So Microsoft obviously decided a while ago that that was done. Most multi-core chips so far are shared memory multiprocessors, SMP machines or UMA machines. They have a single memory shared by all the processors, and communication essentially happens through shared memory. And as I talked about yesterday, the hardware will provide the cache coherence. So let's look at how trends with these types of machines are affecting the resources that are available to the operating system. So here there's a typical configuration of an SMP machine. We've got 2 cores sharing a level 2 cache, and there are 4 cores on this chip, and they go off chip to main memory. If we double the number of cores on the chip, we've got double the number of cores sharing the cache, so this leads to some problems. More cores does bring you more cycles, so you can get more done faster. However, often it's not necessarily proportionately more cache, and almost certainly not more off-chip bandwidth or total main memory capacity. On the network side, again, we have in this picture it's showing more of the interconnect between the chips and main memory and the I/O system. So again, if we introduce more cores and if they're faster, essentially what happens is more memory bandwidth is used as a consequence. And so buses have to be replaced with point-to-point networks or crossbars. And we see the NUMA memory configuration as well to compensate for the contention that's around with the memory access. And basically this means that the interconnect topologies are getting more complicated, and the latencies to access memory are increasingly important, and cache misses are more and more expensive. As the number of processors grows, or the memory demands from each processor grow, like any centralized resource in a system, the interconnect does become a bandwidth. And so as a consequence of more and faster processors, the memory bandwidth also needs to increase. Okay, so what about the NUMA configuration? Here I'm showing multiple CPUs where each of them has some local RAM. And this reduces the memory bandwidth contention, basically because the memory is physically distributed. However, as I said many times yesterday, the time to access memory depends on the location of the word in memory. And so this is where we often see message passing, multiple address spaces, and processors exchanging messages to communicate. And this can potentially scale a lot more than an SMP machine to hundreds or thousands of cores even. Okay, so I forgot I had the animation, right. Adding CPUs brings more, well, memory caches. And you definitely get better locality. So the CPU, the processor only needs to go to memory for in the case of actual shared data, which is good. So the implications of these trends in hardware for software are basically that the performance that we get for free from Moore's law is leveling off. So this graphic is showing sequential performance on the y-axis and a notional year on the x-axis. So historically, we've just been getting these gains, as I said before, by the increases in clock frequency and so on. Now that's leveling off. We're getting more cores, and so there's definitely a perception there that there's a region of lost performance. The software has to figure out how to make use of those additional cores to give us back the slope that we're accustomed to. I mean, you can't deny that software is becoming more and more resource hungry. I mean, there's fancier graphics rendering. We're crunching larger and larger amounts of data, more complicated functionality. Our expectations of software are always getting higher. We never want to go back to software from the 1980s, and so we have to keep that performance trend heading upwards, or else it will feel like computing is going backwards. And I don't think that will be acceptable to a lot of people. Okay, so that's my very brief overview of where we stand with multi-core hardware at the moment. And there's a lot of interesting things written about this. And if that piques your interest, these are a good place to start. Okay, so getting into the specifics, what are the challenges for operating systems given this environment, this context of multi-core hardware? This is a picture of how operating systems today are structured. The monolithic operating system, like Linux, like Windows. So basically, there's an assumption that all the cores are homogeneous. main memory holds the global data structures, and so there has to be synchronization to access global data. But it's a very kind of simple structure. And Windows is an example. Okay, it's simple from the outside, but actually when you dive in, there's quite a lot of complexity within the operating system. So in Windows, this is a kind of picture of how Windows modules are structured. So we have something in kernel space, we have something called the executive, and this is what manages the processes and the threads, memory, the system configuration, power management, and all that stuff. The kernel itself is very small, very minimal, and that does what we think of as the core operating system functionality, the thread scheduling and synchronization, handling interrupts, dispatching exceptions. You could think of the executive a bit like the policy for the operating system, whereas the kernel is the mechanism. So the executive decides how things are done, and the kernel is, holds the mechanisms that are used to do that. And then there's something called the hardware abstraction layer, which is the low-level interface to the hardware, and that's what makes Windows portable. Yeah. So the challenges for operating systems like Windows, I'm going to talk about 4 things in particular here. Amdahl's law, the fact that the communication between processes and between memory and processes is the costs are increasing. The costs of sharing data in this environment, and the diversity of hardware. And the message that I'm trying to get across here is that current operating systems were not designed to scale and were not designed to effectively make use of the parallelism available to them. Okay, so Amdahl's law. If sorting takes 70% of the execution time of a sequential program, and you replace that sorting algorithm with something that scales perfectly, then on a machine with n cores, how many cores do you need to get a speed up 4 times the original? Well, this is the speed up on the left and the number of cores on the x-axis. The top line is showing the speed up that we want, our 4x speed up, but the actual is somewhat underneath that. And in fact, even as you get up to 16 cores, you're not even at a 3x speed up. Why is that? This is the basis of Amdahl's law. So here, f is the fraction of the program's execution time that is infinitely parallelizable. So that's like the sorting algorithm in the example 2 slides ago. We have to assume that the remaining fraction of the program is totally sequential. So it has to execute sequentially. And then the maximum speed up on C processes or cores is defined by Amdahl's equation. So what's going on? Well, looking again at our 4x speed up, we look to the right. The limit as the number of cores or the number of processes approaches infinity is actually only ever going to be 3.33, given that the parallelizable section of this program is only 70%. We've got 30% sequential, and that's going to stop us ever achieving the speed up that we want here. If that parallelizable fraction is really small, then according to Amdahl's law, the limit is only 1.11 times. If it's 98% even, it's still not great. So here we're going for a 50x speed up. Even at 126 cores, we're only at 36x. So what are the implications? Any serialization will limit scaling. Even things like messages that are being exchanged serialized in flight. A lot of people have talked about whether this means there are practical limits to the number of parallel processors. There's a lot of very interesting questions around when the costs of executing a parallel program, the overheads of parallelizing outweigh the benefits. But that's a whole separate area that I'm not going to go into. Anyway, the corollary, a corollary of Amdahl's law is you really want to make the common case fast in your program. The opportunity for improvement is affected by how much time the event that you're improving consumes. So, you know, if f is small, then the optimizations you make are going to have a very small effect. An example of Amdahl's law in the real world is RSS in Windows. So before 2007, the Windows networking stack really scaled very poorly, and the reasons for this were basically no parallelism. The packet processing had to be done on one CPU at a time, and there was no way to balance the overall load of the system, and cache locality was very poor because the CPU where the packets were processed wasn't necessarily where they were subsequently acted on. So the solution increased the parallelism as per Amdahl's law. So RSS stands for receive side scaling, and basically it takes TCP connections, applies a hash function and uses that hash function to decide which CPU should process the packets. It has some clever stuff to preserve in-order packet delivery and a load of other things, but it does require hardware support. So this is the kind of, this is an example of an operating system feature where the operating system designers did not anticipate the multi-core hardware, and so were bitten by Amdahl's law and had to go in and do a pretty substantial redesign or introduce a pretty complex feature that involved hardware support in order to compensate. Okay, the next challenge for software that arises from multi-core hardware is basically just the cost of communication. We saw a lot of this yesterday, and it's still the case today. So in this example, there's a diagram of a machine, a chip called AMD Barcelona, which has 8 sockets and 4 cores on each socket. And it has this kind of weird interconnect topology. So it really is the case that the first socket can send messages to its neighbors below and beside and so on, except for the last ones, which also have this diagonal opportunity. And I do not know why that is. So looking at the memory access latency here, for a core to access its local level 1 cache is 2 microseconds, level 2 15, on a different core, the cache on a different core 130, and level 3 75. However, going to level 3 caches on different sockets varies between 190 and 369 down there. In a table, sorry, those are cycles, not microseconds. If we look at those costs normalized to the cost of accessing a local level 1 cache, when the core has to go to a cache that's 2 hops away, it can be up to 130 times as expensive as going to the local one. This might not seem like very much, but the fact that these differences arise can actually have significant effects in software, because there's a lot of layers and there's a lot of complexity, but when it comes down to it, those differences do matter. Okay, so the third multi-core challenge is the cost of sharing. So I reviewed hardware cache coherence yesterday, so I won't go through. This is exactly the same slide. What are the implications of having hardware cache coherence? Well, basically, when you squint at it, accessing shared memory is essentially sending messages. The cache coherency protocol is causing cache lines to be moved along the interconnect between cores. And any kind of sharing, write sharing of a single cache line means that those cache lines are going to be moving around the machine, even when the data isn't truly shared. So false sharing, which is what's happening when the data is not really shared, but it's co-located on the same cache line. I have a picture here showing what happens. So if Core A is updating variable x in its local cache, x and y are both co-located on the same cache line. Okay, so Core A updates x. Core B has a copy of x in its cache. So as you may remember from the hardware, the state diagram of the cache coherency protocol, updating the cache line will cause the copies in other caches to be invalidated. So out that goes. Now if Core B wants to come and read y, which is not a variable that it's sharing with x, but it happens to be on the same cache line, it has to issue a fetch. X will give it the copy of the cache line, and so on. This will just continue. So the two cores will be bouncing the cache line around, even though all they're doing in as far as the software is concerned is reading two variables that are independent, reading and writing independent variables. So this is an important design feature for software. People, especially in an operating system, the software developers have to be aware of what data might be shared inadvertently and make sure that they deal with it. And they need to understand how their caches are working, how their cache coherence protocol works. So the costs of this, obviously it's generating a lot of unnecessary traffic on the interconnect. As I just said, the designers need to lay out data structures really carefully. If there is false sharing, then essentially those two operations, the read and the write on the variables x and y in the previous example, they're essentially being serialized. And fine-tuning code like this makes it quite complex and requires significant engineering effort. It's actually it can be very difficult to find these problems. It's quite the effects can be quite subtle, and even knowing where to look, it can be quite difficult to find, especially in a substantial piece of software. And of course, fine-tuning to avoid false sharing reduces portability to other types of hardware. Okay, so the next multi-core challenge is contention on global operating system resources. So I want to show you a short video. This is just a 3-minute video, and it's an interview with a guy called Mark Rusinovich. So he's a technical fellow at Microsoft. He currently works in Windows Azure, but at the time this interview was made, he was working in the Windows kernel team. So he was the founder of a company called sysinternals, which reverse engineered Windows in a very impressive way, and developed a whole suite of tools for analyzing performance, for monitoring what's going on inside Windows, which were free, still are free to download, and incredibly useful. Everyone in Microsoft used them. So then Microsoft bought the company, and Mark started working for Microsoft. So here he's talking about some of the internal improvements to Windows 7. So I think this video is a couple of years old, and I've just cut out for the 3 minutes I think are relevant. He's going to be talking about getting rid of a global data structure called the dispatcher lock in Windows 7 and how difficult it was. So I'll play that now. Just make sure I have sound.
That I think is really cool is a really big in the sense that it has been something that as systems have gotten bigger and more, we've got more cores, was rearing its head as a problem more and more, and it was a daunting engineering exercise to figure out how to address this problem, and that is something called the dispatcher lock.
Okay.
So in the scheduler leading up to Win 7, whenever a thread waits on an object or wakes up on an object, whenever it makes a transition like that from running to waiting in the scheduler, there's an acquisition of a global lock called the dispatcher lock. And so if you've got a multiprocessor workload where you've got lots of threads running on the system on different CPUs and they're waking up and sleeping and communicating with each other, the dispatcher lock becomes what we call the hottest lock in the system, which is that lots of threads, lots of CPUs end up spinning waiting for that lock, and you end up not being able to do anything useful while those threads are spinning. And in a 2-way or 4-way system, or even an 8-way or 16-way, that's not a big deal. But as you get into larger and larger systems, it gets into a bigger and bigger problem. And when you start looking at SQL workloads, which is what we see today on larger systems, it ends up being a significant issue for limiting the scalability of those systems. And one of the things that we're doing is looking forward to, we're seeing, of course, Moore's law, where heat and power and density not able to support the kinds of increases in clock speed that we've been seeing, and now we're moving to multi-core systems, and there's people that say we're going to have 128-way systems on our desktop in a few years. In any case, it's a big problem on servers as they get bigger. It's also potentially a problem in the future on client systems. And a guy named Arun Kishun, who's a kernel developer here, kind of a superstar, took it as a kind of a side project to see if he could break it. And Dave Cutler, the original architect of the scheduler, spent a lot of time himself working on trying to get rid of that dispatcher lock. And kind of he moved on to the Red Dog team, which is something also that's been disclosed at the PDC. So Arun took over the scheduler and decided to tackle it himself, and it's one of those cases, I think, where somebody come in with a fresh look from the outside and they're not involved with the original development of the code can see the problem in a slightly different way and figure out a way through it, and he did that.
Outstanding.
And so that's kind of an unexpected bonus. We know we couldn't go in planning to get rid of that because it was such an intricate problem, but he managed to do it.
So.
Okay, so I believe that this business of getting rid of the dispatcher lock actually involved touching 58 separate source code files inside Windows, so it was quite a big deal. Okay, so the final multi-core challenge for software is the diversity of hardware. So we're looking at an increase in heterogeneity of cores. We're going to see cores with different performance characteristics, different instruction set variants, different architectures, specialized functionality. And in fact, we're already seeing this to an extent, and we really can't tune OS design to any one machine architecture anymore. And of course, these changes in hardware are typically happening on a much faster scale than system software, and so the engineering effort to fix the various bottlenecks that arise as the hardware changes are becoming really huge. So some examples, the AMD Barcelona that I mentioned earlier, this is a quad core. There's a shared level 3 cache between the 4 cores, and the other two, level 2 and level 3, L2 and L3 are victim caches, which is a different way of arranging how data moves between the 3 levels of the cache hierarchy. Sun Niagara 2, This has 8 ultraspark cores on the same die, and each core has 8 concurrent hardware threads. And there's an interesting paper which we reference in our paper on Barrelfish about designing a reader-writer lock that was optimized specifically for this particular architecture. But you know, something that's going to work here with this particular cache hierarchy isn't going to perform particularly well on another machine. So here there's a shared 4 megabyte level 2 cache divided into 3 banks, and that's accessed by an 8-port crossbar switch. And then there's the cell processor. So here there's a general purpose core, the power processor element, and 8 specialized coprocessors for data-intensive stuff, for multimedia processing, vector processing, cryptography, and so on. And this, I saw some stuff on the internet that this is has a reputation for being extremely difficult to program. A recent research system is something called the single chip cloud computer. Here there's 48 cores. They're all on the same chip, and there's an on-chip network, and there's hardware support, and there's for message passing, and no hardware cache coherence. So that's an interesting machine. So, in conclusion, these multi-core challenges, parallelism, we've got problems with Amdahl's law, we've got the costs of sharing, we've got the bottlenecks that are introduced by global resources as the number of cores scales, and then we've got these really high costs of communicating, going to main memory or communicating between cores, and added to that this diversity in hardware, this wide variety of systems that's starting to appear, the fact that they're evolving all the time, and that we're seeing heterogeneity within one system. And so, to reiterate, we believe that current operating systems are okay. They're performing all right in this environment at the moment because of tweaks like what you saw Mark Rasinovich talking about there. But they're really not designed. They weren't designed from the outset to deal with this environment. And there's some further reading. This technical report is the report I referred to earlier with Dave Patterson's quote about the brick wall. It's a really interesting read, actually. If you're interested in parallel computing, I recommend it. Okay, so I think I've got about 15 more minutes before lunch, so I'm going to dive into the multi-kernel model, but and then continue after lunch with the rest of it. I won't go through all of it in 15 minutes. Okay, so I showed you this slide before. Basically, the multi-kernel model allows us, it's structured in order to allow us to apply insights from distributed systems to the problems that we're facing of scaling, of diversity, of adaptivity in operating systems on future hardware. So what are these properties of a distributed system that we think the operating system should be cognizant of? Well, obviously parallelism, message passing, state replication, and being able to use all of these features in order to get good scalability, potentially to get fault tolerance, although that's not something we've considered yet in Barrelfish, to get very good locality, so everything that's local is very fast, and to make sure that where there is sharing, as you'll see, sharing is actually inevitable. At some level, in a tightly coupled multiprocessor, there is going to be some sharing. So I'm cheating a bit by telling you it's purely message passing, but I will explain. Where we do have sharing, we should be it should be explicit, and that's something you see in a distributed system as well. So here's a diagram of the multi-kernel model of this notional reference model. So at the lowest level, we've basically got a bunch of heterogeneous cores. There's no shared memory between the cores, at least that's the idea. They don't share anything in memory. Running in the software, we have a small amount of architecture-specific code, which it's necessary. However, the bulk of the operating system functionality is in this general-purpose OS node, which has a state replica for operating system data structures. And the only way that these OS nodes communicate is by exchanging messages asynchronously or non-blocking. So an example of where we are actually going to be using shared memory in this, even in this reference model, let alone in the implementation, is that we need some sharing in order to implement these messaging channels. So the state replicas on the OS nodes are going to need to be coordinated in order to make sure that state is consistent. And so here the multi-kernel model says you use some agreement algorithm to do so. And then above that we have a bunch of applications, which may be local to a core or may span multiple cores. And by the way, the multi-kernel model is not saying anything about how applications share memory. So applications are perfectly free to share memory if they wish to do so. We're completely agnostic about that. We're just talking here about the operating system. So the multi-kernel model is built on 3 design principles, and I'm going to go through them one at a time. So the first one is explicit message passing. Okay, so fundamentally, I mean, we have talked about this quite a bit, certainly yesterday and a bit today. Message passing decouples the structure of the system from the way in which cores communicate with each other. So in contrast to shared memory, where it's all tied up, the way that a data structure is arranged, for example, is very intrinsic to the way in which cores share that data structure. With message passing, we have the communication patterns very explicit, and that gives us opportunities for optimizations and also for debugging and for changing the way that these communication patterns take place. There are also opportunities for things like pipelining and batching with message passing, and we believe that this is a better match for future hardware because it means that we can have heterogeneous cores. We don't need to rely on cache coherency or memory coherency, and it also allows split phase operations, so asynchronous operations, message passing. A message can be sent, and while waiting for a reply, the core can be doing some useful work. So a lot of these things we're advocating here are, yes?
So I imagine it would be a lot easier for the application writer to work with a shared memory model.
Yes.
So will this kind of operating system provide that aspect for the application?
Yes. Yes.
So you still provide that?
Well, so the multi-kernel model doesn't say anything about whether we provide that or not, but in terms of implementation, Barrelfish certainly provides that. And I would imagine anybody, most applications are written that way. It would be kind of crazy not to. Yeah, so a lot of these advantages we can get from message passing are sort of standard things people design, point solutions. For example, data structures that can be updated using only 1 or 2 cache misses on particular architectures, but that obviously has a bunch of the problems that I mentioned earlier. And of course, the great advantage of messaging is that the system is very modular and components only communicate through well-defined interfaces. Shared memory versus message passing. There's a very famous paper from 1978 by Laver and Needham, and they actually argue that although message passing and shared memory are duals, and we saw an example of this with Mark yesterday, in fact the choice of one model over another depends upon the machine architecture, and that's a sort of a very insightful comment given the way architecture is evolving today. So we have seen that shared memory has been favoured up until now, but when we look at it, there are certain trade-offs that depend upon the size of the data being shared and how much contention there is. So I'm going to show you an experiment that we did for Barrelfish, basically to see whether it was ever the case that message passing could be cheaper than shared memory on a tightly coupled multiprocessor, on a multicore machine. So what we did is we measured the latency per operation of updating a shared data structure, an array, without locking. We didn't do any locking, so cores were just overwriting the values that other cores had written. And the hardware was this 16-core AMD Opteron. So the hardware, I'm telling you the hardware because I suppose it's kind of good form, because the hardware matters, as you will see. The way the caches are organized and shared affects the answer. Okay, so for this experiment, the first part, the costs of shared memory. So here the threads are pinned to each core directly, and each thread is updating the same small set of memory locations, the same array, without locking. And so what's going on is that the underlying cache-coherence protocol is moving that array between the caches as necessary. Okay? So consequences of this are that while that cache line is being fetched or invalidated, it'll be invalidated if it's in the local cache and some other cache modifies it, the processor is stalled. The speed of this operation is also limited by how long it takes to do these round trips for these cache lines to bounce around on the interconnect. And so what we see is that the performance depends upon how big this array is, how many cache lines it takes, and also the number of cores that are involved. So here are the results of this experiment. So on the x-axis I've got the number of cores going from 2 up to 16, and on the y-axis the cycles per update operation. And you can see that when there's only one cache line, performance really doesn't change much. It scales pretty well with the number of cores. However, when the number of cache lines goes up to 8, then we're actually seeing increasingly long latencies. And this is purely the effects of the cache-coherence protocol moving those cache lines around. So this is effectively exposing the scalability of the cache-coherence protocol. And of course, while the reason that it takes the cycles per operation increases is because the cores are stalled while waiting for the cache line to get back into their cache. So in contrast, we look at message passing. So here we're running on one of the cores a single server thread, and that server thread is solely responsible for updating the array, the same array that we had before. And on the other cores, other threads are just sending RPCs, sending requests to the server saying, do my update. In the implementation of this experiment, the client threads are actually issuing a particular type of RPC, a lightweight RPC, and it's one of these mechanisms that's tuned to the hardware in this particular case. So we assume that we make sure the procedure call fits in a single cache line. So this, message passing is actually under the covers using the cache coherence protocol itself, which is it's a fairly subtle point, and I don't think it affects the results, but just for completeness, so you understand how we constructed this experiment. So in here we had the clients block while they were waiting for a response from the server. And so here's a visualization of it. Basically, the delays here happen because the requests at the server queue up, and it takes time for each request to be serviced. So the results here, I'm just showing two lines. Those two lines really close together. One is for updating an array that covers one cache line, and the other is 8 cache lines, and they're so close together that I've omitted the other sizes. And so basically, as you would expect, the size of the data being updated doesn't actually have any impact on the scalability here. So the increases that we're seeing are caused by that queuing delay at the server. Okay, so let's look at both shared memory and message passing together and see what happens. So the top line, the red one, is the shared memory with 8 cache lines, which, as we saw before, scales poorly. Initially, what am I looking at here? So the message passing is more expensive than all of the shared memory versions, apart from the 8 cache line version. However, when we have more than 4 cores and more than 4 cache lines, the lines cross, and we actually get message passing being faster. The line at the very bottom is the cost per update operation by the server in the message passing experiment. So basically what's happening there is that the server's getting really good cache efficiency, so it can perform twice as many updates per second as all the 16 shared memory threads combined. So this experiment, so there's more. Remember that I said the message passing version was the client threads were sending blocking requests. If those requests were non-blocking, if they were asynchronous, then essentially the difference there between the time it takes for the server to do the update and what we're reporting for the client there would be spare cycles, and in theory at least, although this is quite hard to implement to do this effectively, those client threads could be doing other work, or those client cores could be doing other work while waiting for the response from the server. I should say, because Miguel has taken me to task over this experiment before, that this is a very contrived experiment. This doesn't necessarily tell you anything except that given this hardware you can contrive to make shared memory be more expensive than message passing. But I believe it does highlight the various the relevant elements, the considerations you need to make to compare the costs of the two approaches. And if our theories about what's going to happen with hardware in the future are right, and in particular if we scale to so many cores that we don't have hardware cache coherence, then we really are moving into a message passing regime whether we like it or not. So I think that's a good place to stop for lunch.